Hey, welcome back. This lesson is going to be about quadratic functions of two variables. So, a quadratic function of one variable is the kind of thing that you're used to seeing written as f of x equals ax squared plus bx plus c. So, this lesson is going to be about essentially the analogous type of functions for functions of two variables, ones where x and y can show up with at most their second power. We're just going to spend this video doing a quick overview of what a quadratic function of two variables looks like and what the graphs of them look like so that you can have a picture in your head when you are thinking about quadratic approximation. All right, let's get into it. So when we're thinking about quadratic functions, we're thinking about functions whose formulas have the variables showing up with a second power. So in single variable calculus, again, what that looked like was a function f of x that was of the form a constant, just a number times x squared plus another number times x plus a constant. So three constants, a, b, and c. And you know already from the years that you've been studying math, essentially what these functions look like. And sort of the prototypical graphs of these functions, well, we know that they're parabolas. The values of a, b, and c essentially determine where they show up in the xy plane, like where the graphs show up. And in particular, the value of a here, the coefficient on x squared, determines whether or not the parabola is a smiley face parabola or whether it is a frowny face parabola, right? This is essentially when a is bigger than 0 and when a is less than 0. You can think of the values of b and c as things that would shift the graph of this function up and down and to the left and right, but sort of these are the two options for like the types of shapes that we could get for a graph of a function like this. So moving on to functions of two variables, the general formula for a quadratic function of two variables looks like this. I'm going to call it q of xy, and it is a constant times x squared plus a constant times x times y plus a constant times y squared plus another constant times x plus another constant times y plus one more constant f. So there's 6 terms here because there's sort of 6 different ways to combine x and y so that you have at most 2 factors in each term. Just like for ax squared plus bx plus c, the values of these constants, a, b, c, d, e, and f, will determine what the graph of this function looks like. And to figure out what all the possible shapes for graphs of functions like this could be, well, it's kind of complicated. It requires a little bit of algebra to figure out like what really are the possibilities. So it's actually easier to just think about like what if the quadratic function that we're looking at only has those degree 2 terms. So ax squared plus bxy plus cy squared. Because it turns out you could take this giant expression, do some light algebra with it, and turn it into something that essentially looks like this. If you're interested, just as a sidebar, the thing that you would do here is completing the square, sort of like how you would complete the square up here to get something that looked like a times x minus h squared plus k. You can essentially do the same algebra to this giant thing to get something that looks more or less like this term here. I'm being very imprecise because I don't feel like going into the details because they don't really matter. But okay, let's just talk about what could the graph of a function whose formula looks like this look like. Okay, so if you were wondering, what could the graph of a function like this look like? What you could do is you could go into GeoGebra, make a slider for the values of a, b, and c, and then enter in this expression, and then play with the values of a, b, and c and see how the graph of the function changes. If you haven't done that already, go do it. It's worth doing just to see for yourself how changing all 3 of these values manipulates the shape of the graph of the function. Anyways, if you were to play around with that for long enough, what you would find is that there are sort of 3 primary shapes that this thing could look like. So the first shape is essentially the 2-dimensional example of a upward-facing parabola. It's the thing whose graph looks like this cup. And you've definitely seen something that looks like this before. This shape is the graph of the function f of xy equals x squared plus y squared. Or a little bit more generally, going back to our quadratic function here, if a is positive and c is positive and b is 0, then you have a shape that looks sort of like this. The cross sections aren't always circular, they could be elliptical. The value of b could be non-zero, and you could still have a shape that looks like this. So if this shape is the analog of the smiley face parabola for a function of one variable, then the analog of the frowny face parabola is the next shape, which is essentially the same graph but flipped upside down. This could be the graph of a function f of xy equals something like negative x squared minus y squared. So something where the x squared and the y squared terms are both negative. Again, the value of b could be not zero, and you could still possibly have an upside down cup like this. And of course, I'll note these are both called paraboloids. We've seen shapes like this all semester. They're sort of like, to me, some of the easiest examples to work with when we're talking about functions of two variables, because they are simple while usually embodying all of the complexities of functions of two variables. So we have upward facing cup and downward facing cup, or we have bottom of a bowl and top of a hill here. These are two of the possible shapes for graphs of functions that look like this. There's one more, and the one more isn't analogous to anything for functions of one variable. It's sort of a new phenomenon that we get when we add an extra variable and look at quadratic functions there. And one way to think about it is it's the thing that you get when you have x squared and y squared, except the signs of them are different. So maybe something like x squared minus y squared, or negative x plus y squared. Up here, if a and c have different signs and b is 0, then you get this third shape. And so if you go in GeoGebra and plug this in, you'll see a shape that looks something like this. Okay, so this is called a saddle because it's meant to look like a saddle that you would put on a horse if you were going to ride it. It's another popular way to describe it is it looks like a Pringle chip. This picture isn't really a good depiction of that, but if you were to go and look on Google for a picture of a Pringle, or better yet, buy a tube of Pringles because they're delicious, you would see that it has the same kind of shape. And the thing that I want to draw your attention to for this shape is that what distinguishes the saddle shape from the other two shapes for quadratic functions is it has these two parabolic traces. So it has a parabola going this way in green and another parabola going this way in red. It's got these two parabolas that are facing in different directions. Looking back at the other two shapes, all of the parabolic cross sections of this one on the left are upward facing parabolas, while for the shape in the middle, all of the parabolic cross sections are downward facing. So they're kind of all facing. So for these two, all of the cross sections are parabolas that are facing the same direction. And so what characterizes the saddle again is that it has two traces that are parabolas facing opposite directions. And lastly, one thing I'll just say to conclude here while we're looking at these three pictures is that what you're going to be doing in your next class is coming up with a formula essentially for the quadratic approximation of an arbitrary function. And just as a little bit of a hint, when we were doing linear approximation, we needed to use information about the first partial derivatives of a function to construct the linear approximation. For the quadratic approximation, you will need to use the second partial derivatives to build this information. Because you can see like in these pictures, the things that are distinguishing these shapes aren't so much the slopes, like the first derivative information, it's more the concavity that's different here. Here we have all the concavity is upward in this left picture, all the concavity is downward in this second picture, and we have kind of two directions with differing concavities in the saddle picture. So what I recommend that you think about when you're doing quadratic approximation is you're sort of kind of trying to figure out which of these three shapes best describes the function that you're working with at the point at which you're doing the quadratic approximation. All right, so that's it for quadratic functions. And again, the thing that I wanted you to take with you is that the possible shapes for the graph of a quadratic function of two variables are the upward-facing paraboloid, the downward-facing paraboloid, and then the last one was the saddle. You'll follow up with this in class when you learn about quadratic approximation of functions. So good luck in class. Good luck if you decide to try practicing drawing saddles. Thanks for playing along. I'll see you in the next video.